Audio check. 1, 2, 3. Audio check. 1, 2, 3. See already that OBS is audio check. 1, 2, 3. See already that OBS is audio check. 1, 2, 3. See already that OBS is audio check. 1, 2, 3. See already that OBS is audio check. 1, 2, 3. Okay, got my mouse back. There we go. That's awkward. Okay, so I think I've already messed this up slightly. I don't want to start and stop OBS. Let's see. Oh, shoot. It's glommed onto the wrong browser window. I need to... There we go. I think that's what I wanted. Okay. We have tricked OBS into showing the correct browser window now. Which I think means we are ready to begin. Therefore, ladies and gentlemen, welcome to the stream of the Discourager of Hesitancy. We are today going to be talking a little bit about some basic programming, beginner programming, fundamental levels of programming. So sometimes if you're intermediate level, some of this stuff as review is good to keep in mind. Last time we talked about a mental model for how the computer works, and the best way to learn how a complex system works is to build it from scratch in a simplified fashion. So that's what we're going to do. Let's go into the thing. All right, we're going to talk a little bit about a fake computer, how it's structured, what we're going to do with it, and get started. Are you ready? A virtual machine. We aren't going to build an entire computer. We can't poke and prod at an actual computer in the ways that we would like to as we learn. We also want a simplified model that we can add complexity to as we go. So we're going to build a process or application virtualization machine. Virtual machine, unfortunately, is a very semantically overloaded term now, with different types of virtualization being talked about. So that's unfortunate. In this case, what we're talking about is we're going to pretend to be a CPU and memory in a program that will consume simulated, fake instructions, and it'll behave as though it were a computer itself. That way we can look at all of its behaviors and modify them as we will. We'll come back around to the Manchester baby towards the end after we've talked about the structure of our virtual machine. But in some ways what we have will be reminiscent of the Manchester baby. So here we go. This will be called the DOE VM. Okay. Structure-wise, we have a lot of options, a lot of different choices we could make. So what I've chosen is a von Neumann architecture, sometimes called a Princeton architecture. It basically means you have one block of memory, and your program itself must live inside of that memory as well. I personally would not have ever structured a computer on a von Neumann architecture. I would have preferred the Harvard architecture, which has one set of memory for your runtime and one set of memory for your program instructions themselves. A lot of possible exploits are due to you forcing jumps into code that was never intended to be reached or in states that should not be reachable. And to do that, it means, yeah, it's not good. So a von Neumann architecture is what we're going to use because it most closely simulates what we're looking at in modern CPUs. I don't know of many modern CPUs that don't have a von Neumann architecture. We are going with a register-based virtual machine. You can have a stack machine. Java VM is a stack machine. I'm going to post a little caveat there. The Java VM was a stack machine. Now it is partly a stack machine and partly something else because a stack machine has some inherent slowness to it. And to get performance, there are a lot of cheats and hacks that are not stack-based that JVM uses to make its code more optimized. It might behave a little bit more register-like in cases than people suspect. But we're just going straight for a register-based because that most closely simulates a real CPU. Register machines actually come in a number of varieties. What we're doing is what's called a random access register-based machine. It means that we have registers. We can otherwise access all of memory randomly. We can access our registers randomly, arbitrarily, I should say, not randomly. So there's no inherent order in memory or in the use of the registers. We are going to execute bytecode. We could have our virtual machine interpret something that's not bytecode and execute it, but we are going to use bytecode. There's often a fake assembly language that goes with a lot of virtual machines. This one won't have one. It will be bit by bit, which kind of brings us back to the Manchester baby, which we'll talk about again at the end. Okay, so our choices are, our program will live in main memory. We're going to do registers, and we're going to have bytecode that we execute. Some other decisions are fixed size instructions. When we build up the set of instructions our virtual machine is going to execute, they will be fixed size. They will all be the same size, every instruction, which has some upsides and it has some downsides. We'll talk about those in a minute. It's not the only choice. We could go for variable sized instructions, which is in fact what an Intel x86-64 uses, but we're not going to support that because it simplifies things enough for us to get the ideas. We are going to start with 1 kilobyte of data. We're going to start with 16 registers, and I'm going to declare that register 0 is the program counter. Okay, so register 0 is not for us to manually store values in or read values out of yet. It will automatically do things. Okay, the register 0 will be managed for us for now. And that is pretty much it as far as the structure of our virtual machine. The instructions will all be 32 bits. 12 of those bits will be the opcode. We'll talk about what that means here in a minute. And the remaining 20 bits is to pass any parameters to the CPU that we want. This does mean, for simple instructions especially, there are going to be wasted bits. This is one of the reasons not to use a fixed size instruction set. A lot of operations, the length of your operations has to be as long as your longest instruction. Everything that uses less is wasting bits, wasting space. On the upside, you always know where your next instruction is. You always move forward the same amount to the next instruction. Whereas with a variable width instruction set, you have to process the current instruction to know how many bytes to move forward to the next instruction. So again, trade-offs either way. Modern CPU, like the Intel, is a variable width instruction. We will go fixed width. Some basic operations. The opcode, 12 bits worth, will be, if it's all zeros, that's a no operation, means do nothing. If you pass an FFF, then we will take the value in a register, and that will be what we return as we exit from the virtual machine. We're going to say that E means load a value into a register. So this is going to take a 16-bit value and load it into a register. But our registers are 32 bits, so that puts it's basically the lower 16 bits, which means we can represent numbers up to 65,535, 0 to that, in our register directly. The upper bits will always be zeroed, okay? Which means we're gonna have to get very clever, probably tomorrow, if we want to load a larger value in than that. We'll get to that when we add more operations. The opcode D00 is going to be load some address from memory. We'll need some mode information to figure out the address. Take whatever address that is in memory and shove it into our register. C is going to be store. So we're going to take a value in some register and we're going to dump it into memory at some address, and again, we need a mode to figure out this address. We'll talk about address in a bit when we implement it. And then B will be print, some print mode. This will be different from this mode. We'll have to detail all these in a separate document. But it'll print whatever value is in a register. And that's basically it. That's everything we need to start implementing this Do VM. This code will never be available. I'm not putting it on GitHub. Since this is a beginner's course, I will do it all in front of you, but it's up to you to type it in, make it work, test it, debug it. The learning experience is far more important than having a working VM. If the only important thing was you having a working VM with our spec, then I would just give you the code and the executable and it would be no big deal. But we're not going to do that. This is more targeted towards beginners, so take the time, do the learning. G. Finelli, welcome, welcome. I am doing great. We are getting to the fun part. As I imagine this mini lecture series, I've definitely got some changes I need to make to the lectures, but this is kind of where we start with actual homework assignments of writing code. And this is where it gets fun. I sort of imagine this series going on for a long time where we build up this whole virtual machine, we code it all by hand and it's horrible, and then we move into the second stage, which is writing a compiler that generates our bytecodes. And then we do a final segment on optimizations on all parts of it, where we optimize our virtual machine to run faster, we optimize our compiler to run faster, or to generate faster code, all that stuff. But that would be like a year-long course, and I would need a lot more time. But it sounds like in my head, with what I know now, I wish this is how I had been taught. Like I said, it needs a lot of refinement, but I think this would be a more instructive way to teach. I think it would be more fun too. Okay, so we're going to skip out of this, and we're going to start implementing this. But first I have to get my mouse back because OBS has stolen it again. Where is my mouse? There it is, over there. I have to guess where it is based on the hover events on OBS. Okay. Nope, missed. There it is. Okay. All right, got my mouse back, which means we can get this back. Okay, and we're going to start a new project. We're going to close that. Close that. What do I have open anyways? I'm going to close that. I'm going to close that. Okay, so we have nothing in our Emacs right now. You can use whatever you like. We have our machine specification, and we just need a place to work. So active projects. We are calling this Do VM. I will need to generate better instruction set architecture documents, but you know, if I'm cranking out one lecture a day and interrupted, I don't really have time to build that all up, but we're going to have some fun here. So let's go ahead and give ourselves a main dot C. We're going to type in pound include stdio.h so we can output things int main, int argument count, character star star argument vector, which I think is a terrible thing because it's not a vector. Terrible naming. Printf go virtual machine. And then we will return a success code of 0. All right, that's that. For now, I will put this, get a new shell open, so there's no history. We're going to gcc the file main.c into dovm.exe, and that worked. Now we can execute our VM, which does nothing but print its name out. Perfect. Here we go. All right. So one thing I want to do is separate my code into logical pieces. All right, we're going to decompose the problem. That's one of the things we talked about earlier, decomposition. One thing I don't want is a big bunch of clutter in this. I don't want this one file to be 10,000 lines of code. I want this file to be very small. So the first thing we're going to do is we're going to make a dovm header file. And we're just going to start with an empty one. And then over here in main, we will pound include our dovm.h. So in C, there's two different ideas that happen. One is declaration and one is definition. A header file is usually used for declaration. I declare this thing exists to the compiler. So when I'm in main, whatever I declare here, then I can use here. I can say, I know this is defined somewhere, and here's what it looks like. Okay, so first thing we're going to do is pound include pound if not defined. We'll talk about this in just a second. If not defined, dovm h. There we go. All right, so let's talk about what this means. In C, you can only declare a function or a variable one time. So if I say int x, and then later on in my code I say int x again, or even if it's a different type, right? Float x, the compiler is going to say, whoa, buddy, you can't declare x here because we already have it here. So if we are including this header file in a lot of places, the compiler will say this is defined multiple times. So what we do is when we do a pound include on a header file, we wrap that header file and say, was this symbol, which shouldn't be generally usable, right? So I put underscores all over it. You're not supposed to type this in all over the place. If this symbol is not defined, define it and move, and then here's where the end of the if is. This all happens in the pre-compiler. So in main, when it gets this, it literally just puts this stuff right here where this is for me. Okay, so in another file, if I also pound included this virtual machine header, then it would say the compiler already knows this value and it won't execute all of this stuff again. So in other words, this stuff only gets defined once and we're good to go. So that's all that is. And what we need is a virtual machine and that virtual machine needs memory. So we have to decide what that's going to look like. I said it's 1 kilobyte. So let's see here. A kilobyte is 1024 bytes. But we're going to organize it in 4-byte words. I don't know what, well, oh, come on, UXE, there we go. So memory will be unsigned integer 32T array. Like that. And that's our memory. Is that correct? I'm not sure that's actually correct. Or it'll work for starters. How's that? It'll work for starters. The next thing we need are 16 registers. And that's basically it. That's basically all we need. So it's very, very simple. So here in main, we can say, give me a do VM, which we will call VM, right? So this is the type and then the name. And we can do things with this already, just not very good things. So VM dot registers 0 0x 08x, and then the value. So we can see what's in register 0. But now our build gets more complicated. Are you ready? We can't build main until we know what do looks like. So we're going to say do vm.c, which doesn't exist yet. You gotta make that too. So we have do vm.h. This is where we declare things to exist, and here's where we define what they mean. So if we say, make a function called 0 registers, and 0 memory, we declare them here, we define them here. Hopefully that makes sense. Then we can say VM at registers. Suppose we need static const int do VM register count equals 16, and do VM memory word count is 256. I'm going to go ahead and put in size 1024. VM memory size divided by 4. Maybe do VM word size is 4. There we go. These are all things we know at compile time about our virtual machine. So this 256 is actually dovm memory word count. And this one is dovm register count. Now we can just blaze through the registers and zero them if we want to. So for int index equals 0, index less than dovm register count. That's basically it. So we take the virtual machine and we say for every register that we have, set that register to 0. So easy peasy. For memory, dovm mem word count, memory index at index equals 0. Okay. So in main, let's see here. This is one of the reasons I tend to use C++ instead of C. It lets me not have so many naming collisions. So you go memory. Let's go ahead and print memory as well. Memory at 0. And we can print that again. All right, let's see what happens. So we need to compile one compilation unit for our dovm. So we're going to go gcc dovm.c. We're going to say, don't compile an executable, compile this into an object file that we can use later in our compile. Ooh, that's right. dovm.h. We need to say, we need standard integers. Variable modified memory at file scope. So it doesn't want these to be static constant. Okay. Some of the rules I tend to use in C++ aren't available to us here. Just my old habits coming through here. We're going to let the precompiler handle all that. Easy peasy. Okay. So one thing it wants us to do is use the word struct dovm in everywhere, and I don't like doing that. So we're going to tell our compiler, hey, we're going to define a type. We're going to type def this structure as dovn. So what would normally happen, let me just show you this is like a shorthand, if you will. You have struct xyz, whatever. Then we could type def struct xyz as xyz. Because otherwise we would have to type struct dovm everywhere. And this is basically a shortcut to this. So it says, I'm declaring a structure, and I want you to know that this type is called this. Then I don't have to use struct dovm everywhere. So we're going to try that. Build it again. It still wants parentheses before, oh, not an ampersand. Not the address of, I want a pointer to it begin. There we go. That should fix most of that. Okay, so we now have a .o file called dovm.o. We should look at it. Look at that. It's beautiful. It's compiled. It has some of those sections we were looking at in an executable earlier, but this only has to do with the code in those two files, that header file and that .c file. So now this is ready to use in our actual compile. So let's see, we're going to take main.c. We're going to also compile dovm.o and output that as dovm.exe. So we can include multiple files here. Main contains our entry point, which is the main function. And dovm contains all the information that we'd already defined somewhere else. And we can compile those two things together into here. It's complaining undefined reference. That could be because we didn't prefix this. Dovm. So we have to recompile our .o file, our object file, and then recompile this one, and it worked. dovm.exe. Okay, so you can see when we started off, register 0 had 0. We zeroed everything, and it's still 0, but memory had something in it. FFFFCB10. This is a junk value. Your computer doesn't initialize memory. It says, here's memory you can use, but it doesn't set anything. It leaves it as trash. So after I ran 0, it set it to 0. So if we look at our main function, here's where we had trash in our memory. This is technically trash as well. The fact that our trash happens to be 0 is consequence. But here we actually set it to 0. And when we print out the second time around, then we get the 0 value we expect here. Does that make sense? All right. Now, that's not quite how we want this thing to work. So let's go back to the dovm. Our registers need to behave a little differently. I need to be able to access registers as either integers or as floats. So we are going to make a union called register. And a union will let me overlay an int32 and a float. So these point to the same memory, but interpret it differently. So now instead of this uint32 t registers, this is a register array Do we want unsigned integers as well? I guess we do. So we have signed integer, unsigned integer, and a float. All different interpretations of the same thing. Okay. Now we have to change things here, because these registers now I have to tell it which version I want it to look at. If I said .u or .i, this will be the same in the end, but the .f would also end up the same value, but that's only by coincidence. So we're going to say this is all zeros here. Okay? Cool, cool. And that shouldn't have broken anything, except in main we also have to registers.u. We have to rebuild it. So now I'm not a huge fan of rebuilding every step all the way. Okay. Typo. There we go. So we're going to streamline our process just a little bit. When you start doing multiple build files and it gets very complicated, which ours will eventually, well, it'll get more complicated. I don't know if it'll be super complicated. We're going to make what's called a makefile. And what we're going to do is we're going to set these commands in our makefile under different rules. So we're going to say a rule called build all, and it depends on main, and it depends on dovm.o to build it. Those two things have to be there, main.c and dovm.o. Then you put a tab. It has to be a tab here. And we can say this command. Okay? But we also have to tell it how to do this. So we make a rule for that. And we give it this command. gcc, blah, 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 blah. Okay? So when we run all, the all rule, it'll say, does main.c exist? Oh, it does. Does dovm exist? This object file exist? Oh, it doesn't? Then I need to go build it. This depends on dovm.h existing and dovm.c existing. Okay, and it'll check and say if the .o file is older than the modified time on these files, it'll rebuild this for us. Okay, so when we run all, it says main exists, it's fine. dovm is a rule we know about. So we go check. Are these files newer? We have to rebuild it. Or if this doesn't exist, it'll rebuild it. So this now should just work. If we go to shell and we say make, you'll see that we didn't make any change to the dovm code. So it didn't have to rebuild that, and it just runs this command. Okay? We should be able to run it, dovm exe, and there's the same setup we had before. Perfect. Maybe in main we can say 0 things or something. So now we can make, and it works fine. Okay. Now, our virtual machine needs those operational codes. There are 2 ways we can do this. Operation codes from the slides, which I will post up after we're done. We can do this several ways, actually. We can go with pound defines opcode no op is 0x000. Halt would be 0x fff. We could do it this way. This is probably how I'll do it for now anyways. So a pound define doesn't write code. This happens in the precompile step. So in the compiler, whenever it sees op no op, it'll replace it with this text. So here, if you see do VM memory word count, it'll replace that text with this text. And then it'll say, oh, well, this is text that needs to be replaced, and it'll go find that text. And this is text that needs to be replaced, which is this text. So this is math and code that's all generated exactly at compile time. Anytime you see these pound statements, those are pre-compiler. Before the compiler gets a hold of it, make these substitutions. So op halt, op load I. Talked about why we chose that name later. That one is E. Then we have the other load, which is D. Then we have store, which is C. And then we want to print. Which is opcode B, 0, 0. Okay. So if we zero our memory and then execute it, it's just going to run no ops the whole time. Okay. Let me think. We have some different things we could do here. Let's start at the easiest level. Do VM execute. I'm going to type def and instruction from U832T. So that says this type here. I'm going to sometimes call it instruction, but you know that this is what it really is. So we're going to execute an instruction. Probably should prefix it, do VM instruction. Instruction. Okay. This is our decode stage. Okay. We're going to say Win32T opcode equals our instruction and those 12 bits off the end. So basically every bit that's not on the end there gets masked away, and bit shifting it by 20 bits. Then we will execute different code depending on what the opcode is. Okay. So case. Oh. Probably should prefix all these ops as well. So we're going to say get the opcode out of our instruction, just basically snag these 12 bits, and then say what is our opcode. If it's no op, I would like stdio to be available here. So I can print f. No op. Halt. We're just making sure that our decoder is putting us in the right area. Load immediate. Load from memory. Store and print. Okay, so we're not really fancy here at all. And we can do things like do VM execute. We're just going to pass in those opcodes, right? Do VM opcode no op. And then you have to bit shift that by 20 so then it's in the right place. Because our opcode, that's how these opcodes work. Alt. Load immediate. Load from memory. Maybe we do call it that. I think I like that. Load from memory. Load immediate mode. Load from memory. Okay. Store and print. That should just about be everything we need. Let's see if the decoder is working up to now. Remember, I wrote this make file, so it should figure out that I need to recompile my dovm.object file and my main. It is trying to unknown type dovm instruction. I'm not consistent in my naming, apparently. There we go. So it rebuilt our object file, and then it used it in the next build. And we run it. So here's our register 0 and our memory address 0 at start time. We say we set these registers to 0, then register 0 is 0 and memory 0, 0. Then here are the opcodes as they're executed in theory, and by executed we're not doing anything yet. We will get there. Okay. So let's make things interesting. We can do this a couple of different ways. Void do VM op no op. Because no, it doesn't do anything, so we don't have to do anything. We'll just go to halt. Let's go to halt. I'm going to take the do VM instruction, pass that in. So we have halt, load immediate, load memory, store, and print. Okay. So we declared these above. So down here, I can just use them. Do VM operation halt. our instruction. If you don't declare it first, you can't use it. This one goes away. No op does nothing. Halt. Load I. Go to M. Store. Now we have to tell it what to do with each of these. We have to define them. They've been declared. Now we must define them. Right, halt isn't too bad. We have to actually update something. dovm.h. Our VM needs to know if we are running. Hey, good afternoon, Javest. How are you doing? We are building a little tiny virtual machine so we can start simulating different things with a CPU. Well, with a computer. That's our plan. I don't need these right now. I'm going to comment them out. You don't need them. As long as we remember that we have trash values, the rest of it doesn't matter. But we should VM, what's here? Do, VM, init, RPM. One more small change. Is that? Because the instruction needs to act on the virtual machine we're running. I'm good, thanks. How are you? Did it work out with the cow meat that you bought? Yep, it's all in. 600 pounds of cow in my freezer, ready to eat. Once we thaw out what we need to. Okay. Delicious, delicious cow. I love meat. Meat is excellent. Okay, this execute is not quite accurate, but we're gonna just use it anyways. So no op doesn't do anything. Halt. Load, store, print. So I'm gonna put this in here. Halt. Print. Store, because we're gonna do a little bit of decoding in each of these instruction handlers. Where load and store are actually the most complicated. Load and knit isn't even that bad. The only thing that doesn't need one is no op. Okay, so when we halt, we need to know what the register is that will be our return value. There's two things that happens. Let me put these in. All of our declarations and implementations have to match. We need to get a register from our instructions. So register equals our instruction, and we want to skip those first 12 bits. We can skip those 4 bits as well and just get this byte. Oh, we don't even need a byte, really, do we? 1, 2, 3, 4. I mean, we could just steal those bits. Then bit shift them by 4, 8, 12, 16. So halt, given whatever's in our register. Then we can actually look at it. VM.2 registers 0x minus. We don't want to do that. Let's not do that. Print the register number and be done. Okay. Load immediate needs a register. And then uint 16t. You know what, we can be really strict here. 8t. When we get a register, let's make sure it's an 8-bit integer, unsigned. That's all we really support anyways. We don't even support that many, but value equals. So this is the immediate value, which we're going to just take from the lower 16 bits of instruction. And 0 x 1 2 3 4 1 2 3 4. We're just going to take those lower 16 bits. Load I a value into register $ register value register. Okay. Nice. When you first mentioned you bought a cow, I thought, why are you going to start a farm or something? Yeah. So unfortunately, buying a cow means 2 different things. You can buy a cow and put it in your yard and feed it, or you can buy a cow. So instead of buying beef, where you buy it by the amount of meat, you instead buy the cow. So when they kill the cow and hang it, you pay for the hanging weight, and then you pay someone else to process it, which, to butcher it. And so you often end up with about 60% of the hanging weight as meat, but you paid for the cow, so you got all the other stuff as well. So you pay for the hanging weight of the cow, and then you pay the processing fee. And it turns out that your beef is a lot cheaper when you do it that way, and you got your freezer full, so you don't have to go to the store and buy more beef. So when you buy a cow, it means you're buying the whole cow and then paying someone else to process that cow down to meat, down to beef. So yes, good times. Load M, I kind of don't want to deal with, and same thing with store a little bit. Is that true? How do I feel about that? That's actually, yeah, very true. I really don't want to deal with load right now. Or store. Well, store's not as bad. We still have to do the whole address thing. We'll come back to that. Print. All right, here's the deal. I want a print mode, or print type. Output type, output as. These 4 bits will tell us what to output it as. And then we need a register that we're going to output. So we're going to get these bits here as our register. I'm going to print I'm going to give myself a little helper here. Is that true? Char star print types as an array equals. So we can say we want to output an integer an unsigned integer or as a float. We might as well do character this time. It doesn't cost us anything. So these things can be defined here and declared here, not in dovm.h, because I don't expect anyone else to use it or access it, so it's fine if it's only in this file. It doesn't have to be shared in the header file. Yes, nice. I've done something similar in the past as well, and yes, it's much better value for the meat, and I also like purchasing and supporting local farmers. Yes, exactly. The guy we bought it from, it's like his first year he bought 2 cows and he just sold them because his freezers are already full of other meat, deer and elk meat. But yeah, it's been completely grass fed on natural grass, and I've driven up and seen his cows. I've driven past him before and said hi. So yeah, it's way better. Good quality meat ends up being good value. The other thing I want to do is print type int uint is 1. Float 2 char 3. I don't know how I feel about all this just yet. We'll refine as we go. So we're gonna print a thing out of register something or other. So our print types given our output as, and then we need the register number. Okay, so we should be able to try some of these. This load from memory and store are a little bit weird, but we'll come back around to those. So in theory, no op and halt. So everything we expect to be just zeros. So if we make, no, it doesn't like something. Oh, I forgot a comma. Instruction. Oh, yep. So here we need to pass the virtual machine as well. Okay, it does not know what Boolean means. That's fine. I kind of expected that. One of those C, C++isms I kind of mesh together. Not a big deal. Running is 0. I thought I had halt. Oh, I didn't. Oh, interesting. VM running equals 0. There's so many different ways you could do it, and I really haven't designed it. We're sort of discovering it as we go. Halt, 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 halt. can do that. VM exit code 0. VM exit code equals our VM registers at registered dot signed integer. Right, because our registers we have to treat different ways. Rename buffer. I don't know why I did this, but okay. Make. Oh, not great. Too few arguments. That's true. Address of our VM. There we go. So our registers are full of junk values. So no op doesn't do anything. The halt happens to have a 0 in those bits where you specify the register that will contain our return code, our exit code. Load I has a 0 in some of our bits, and this is a completely invalid register number because we had trash floating in our memory. Load M we're not doing anything with. Print happens to return a signed integer. Print signed integer version of whatever's in register 0. So we're slowly getting there. There are a couple different ways we could go. I want to load actual instructions in. So maybe what we need is a way to say int instruction count. So when we init, instruction count equals 0. We don't need an instruction, any instructions in there. Execute VM. So we're going to fetch, decode, execute. And there's just so many ways we could do this. I kind of want to maintain that fetch, decode, execute. Oh, instruction count. And we also need, no, we don't need, we're good. So we talked about this yesterday. Fetch, decode, execute, advance. So VM registers 0, moves forward by 4. We're just moving to the next instruction. Execute's going to be a little bit different. We're going to come back to that. Fetch. Instruction equals underscore memory. No, not VM memory. We're going to go into our memory banks at our program counter. So VM register 0. Gets me an address into memory. And then we get that value, and that's our instruction. Decode, it's basically this. But we're going to do something slightly different. just to keep it clean. We're going to use a function pointer. Now let's forget the syntax, so just a second. C function pointer. It's just a syntax question, not a conceptual question here. I think return, so our return value is void. We have a pointer to an op code handler, operation handler, instruction handler, and it will take these things. Is that it? Come up here. We have our op code, our op handler is null pointer. Ooh, let's see, probably null. Instead of this, I'm going to say op handler equals go m op no op. Talk about this in just a second. And when we execute the brace op handler given our VM and our instruction. There we go. Now the flow looks a lot more like our diagram. From before. That makes sense? Let's see, where's my thing? Here we are. Fetch, decode, execute, advance. Basically we said our op handler is a function, but we haven't told you which function yet. I'm going to come into this switch case statement. I'm just going to get a little bit out of hand here eventually. It's always going to do, it's going to tell us which function we actually want to use. So let's just line it up so it's easier to read. Because this is going to get quite full of things eventually. Okay, so if it's a no-op operation code, we use this function. If it's a halt function, we use this function. Which means we do actually need this. We'll just be consistent. Okay. What else have we got here? Fetch, decode, execute, advance. Program counter equals. If program counter is greater than the VM's instruction count, we're going to do some other things. and return. What we need to do is kind of like let's a halt. But maybe we do an error. So let's make a function for error. VM error. And I want the VM, because we want to halt it. We want a error code, so in32t error code, and then we want an error message. Let me put that just anywhere. Error message. I'm going to put the error code in as well. But the main thing is, we turn running to off. We exit with an exit code. Except that this exit code is the same as the error code. All right, so if we are executing and our program counter is outside of our instruction count, then we will do VM error, and we're going to call it error1, program counter out of bounds. Some number is greater than or equal to some number, which will be time for some coffee. I don't blame you. Sounds good to me. The program counter and the VM instruction count. We actually advance one word, so it's fine if we do it that way. Anything else? If we put back in those 0 options, it might actually be a little safer to do a couple of tests without writing what needs to be written in here. All right, main while VM running go VM execute, which actually changes the way we do things here. Execute. Now we don't need this instruction. We're getting the instruction ourselves. We need to start it. Which actually looks a lot like this. So maybe we don't need to initialize anything. I'll think about it. Except here we set running to 1. We're going to start our VM. As long as it stays running, we execute the next command. We probably want to zero things just for starters, so that all of our inputs and outputs are as expected. Make. Oh, that's right, instruction. Okay, we're getting close. Execute 20 arguments to error. Oh, yeah. We're not going to deal with this just yet. We're going to keep our error messages very simple for a little bit. All right. 47. Line 47, we did not do a thing here. Add our program counter. Run our make. Registers plus equals 1. Oh. So during our advance, we have to specify it's a union, so we have to say it's the unsigned integer thing in there that we're interacting with. Error message undeclared. Okay. Hey, there we go. That's nice. So this should run a whole bunch of PC out of bounds. Oh, we have no instructions. That's correct. Actually. So we make, execute, program counter out of bounds. And then lastly, instead of returning 0, we want to return our vm.exit code. So make, run it. Now, when we look at our return code, $sign ? We got our 1. Cool. There, we have the fundamental structure of a virtual machine. Now, I have two thoughts in mind. Right now, all of our instructions are 0, and we don't have an instruction count. So we could fake this. We could say vm.instruction count equals 2. Make and run. Oh, interesting. Oh. No op, no op, and then we're out of bounds and have to exit because we told it we have 2 instructions and they're all 0s, but now we're going to pop out because of an error. Perfect. If we want to test these, we need some convenience functions. So I don't think I need these ones here. I think we'll put them in the implementation file and it won't make a difference. These don't need to be here. Initialize, start, execute, running exit code, etc., etc. Okay. Well. We want to be able to add operations. So void dovm add no op. So basically these things. just need to be modified a bit. A no-op doesn't need anything. A halt needs uint 8t register. Load immediate needs a register and a uint 16 t value. Load depends and store. We're just gonna leave those alone for now. And print, we need to know the out as and the register. Output as. So basically we're going to say, I imagine mostly these are only going to be used for development while we're testing. Later on we'll add full files. But in the meantime, add a NOAA. VM memory app VM instruction count equals 234 1234 0. That's adding a no-op. And then we move forward one. Okay. Halt. Instruction count equals do VM op halt bit shifted 20 let's see, 12 22, yeah, 20 pixel 20 bits combined with this register. I think the register is not very big, or not, it's offset by 16 bits if I remember right. So when we do a halt, yeah, we get that 4 bits right there. One thing we should do when we get a register. No, that should be fine. That should be good. Register less than bit shifted. That's it. That's it. I guess. Okay. Load immediate. Board with our value. Load M. We shall just ignore that. This is a load I. Thanks for making the computer build up our instructions for us a little bit. This is not a halt. This is a halt. We can be consistent. Even though it's all zeros. Op, no op. Doesn't make any difference because it's all zeros. Store. Again, we're going to have to come back and revisit store and load. Print is an interesting one. It's more like this. Except I'm not sure the register is where I think it is. Let's see if we go to the op print. The out as is shifted 16 and the register shifted 12. So in theory, we're getting there. So instead of setting our instruction cat, we're going to initialize. Then we're going to say do VM add no op to our VM and a halt, which will get the contents of register 1. So that should be 2 instructions. It should no op, it should halt, and then it should actually exit with error code with a value of 0. Let's see what that does. Make, of course we have some issues. Did I mean you int 16? I did indeed. Make it again. This definition 0 registers. These don't need to be functions at all. They're too simple to care about. There we go. That's how much do VM. In theory, it failed. We init, we add stuff, we start. I think that's correct. So rebuild, rerun it. Hey, there's our no op and our halt with whatever's in register 1. Echo $question is a 0. Cool. It is starting to come together. We just about have some load and store operations working. Load immediate. Into register 1, the value 42. Then we're going to halt based on what's in 1. We'll run it. Register, then value. Interesting. Okay, so no op, immediate load into register 0. So I'm doing something wrong in add load I. One other thing we can do is say what instruction we're actually at. VM registers sub0.u. so we know what instruction we're at. I'm going to do all this now before I regret it later. There's some things you just kind of want in place right from the beginning. And understanding what's going on is good. Okay. Build. And go again. There we go. So instruction 0 is a no-op. Instruction 1 is load I something. And these are trash values, clearly. And we're going to halt. Oh, we didn't set it thing. M_register. No, not M_bm. Registers at reg.u equals our value. Make and run. Not register 0. Oh, it is. And then reg should be 1. Reg bit shifted 16. Oh. ORed with reg bit shifted 16, ORed with our value. This print make. There we go. Load into address 1. No. Load the value 1 into some garbage register. Register then value. Register then value. Register then value. So when we're running this pop load I, register and a value. Put a value into a register. That might help. There we go. Load the value 42 into register 1. Alt $1. Echo $question is 42. So we are getting our return code all the way through. So we can now load immediate values up to 16 bits. Perfect. What's left? Load memory and store memory. Let's start with store memory. That'll be a little bit easier. We also need to do some more, well, we'll do some print stuff as well. That will also be good. Here's the deal. A store is something like this. $sign or register. It's shoved into memory some address, right? We need the register. We also need a, oh no, we don't. We don't. So we need an address. Address part 1. Not this one, actually. Address part 2. 8 bits. Last thing we need is my mode information. Okay. So what's going on here? Sometimes we want address part 1 to be an actual. So sometimes the common usage is we have an address stored in our registers, and then we have an offset which is not a register value. So this would be $3 plus some offset of like 4. $3 plus offset of 4. That kind of thing would happen in here. So I need to be able to say the part of address 1 is it an immediate value or not. And these can change a bit depending on what we're doing here. Okay, so if modes and 0x, so we really have 8 bits, and we can turn on or off 2. So we're going to go with 1 here. Else modes and 0x002. So we're checking the next bit over. Else. Register 1 equals that. Register 2 would be that. Then your actual value of memory, you get 32T. well, no, here, address 1 equals our VM register let's actually get a little bit complicated. That's okay. Registers at register1 dot u address 2 register 2 otherwise address 1 equals ff bit shifted 8. This one would be ff not bit shifted at all. There we go. That's not right. Registering 2, bit shifted 8, address 2 at register 2. There we go. Phew. Okay. And this print actually gets more complicated. So what we're going to do, we're going to start with this part up here. We're not going to put a new line because what happens next is here we either do a register $sign modulus D plus, so we want register 1 register 2, or we just want address 1. Address 2. There we go. Which means that happens there. That happens always. And that's a store operation, basically, which is a little bit complicated. So if we add the store operation, this gets complicated. Good evening, time to learn some programming again. Nice. Welcome, welcome. We're building a small, teeny tiny virtual machine to simulate a basic computer. Very tiny. We're going to use that and build on that and refine our model over time. It's a register-based fixed instruction size von Neumann architecture. We have 1 kilobyte of memory and 16 registers. And so far, I think we've got how many opcodes? 1, 2, 3, 4, 5, 6 opcodes. So pretty simple beginning. We're gonna get load and store working, add a couple more bells and whistles, and then call it a day before we do math, bitwise operations, and logical comparisons tomorrow. in theory. And how is your Onyx engine looking? I didn't have time to pop in today to look before I came to stream. Had a business meeting, so didn't have much time to get things ready. Our virtual machine so far is very rudimentary. We can initialize our VM, add some instructions to it. So this builds up the binary bytecodes for us for now. And we say start, and as long as it's still running, we execute the next command. And at the end, we return our exit code. So very simple. Adding Tracy profiler, place some more instrumentation tags and trying to figure out how to group tags, etc. Have systems. Yep. Organizing a profiler turns out to be a trickier problem than people think. Tracy's not very good at it. Got to work around. Okay. With instrumentation in place, move to render command queuing. Ooh, to separate your threads. Ah, that's fancy. I thought you were just about at the point of building a demo game in it. in Onyx. There's always one more thing to do before you can do that, right? Okay, so let me think. Store. Oh, so you did all that store work and then we didn't actually implement it, right? There's the print, which means we can now do VM point to memory at. I'm gonna kick myself later for this, aren't I? Keep everything word aligned or not? Oh my goodness. Suns, they're a little crazy today. Yeah, I enjoy building those systems, but eventually, maybe 2030, I can come around to a game. Yeah, yep. That's how it works, right? So we're going to take address 1 plus address 2 equals VM.2 our registers at am I not snagging the 12-bit opcode. We have 4 bits of mode. Well, shoot. I don't have enough bits. I don't have enough bits. I run out of bits. Unless top bit of each mode is its each address part is the mode. Now there's just not enough time in a day for all the different things we want to do. Too many hobbies, too many cool projects, too much fun. Now, a register only needs 4 bits to be specified. We don't need more than that. So we do have a floating bit, which means we actually have 7-bit literal offsets. So maybe that's the way to do it. No, we do want these 2 things back. First thing, we need the register that we're going to store, which is those 4 bits, 16 offset. So there's our register. So we're going to store whatever's in register, whatever, into memory. Where address 1 part is here. I'm just trying to think how to fit all the bits in we want. We need address 1 and address 2. We have the shift address 2. Then we say if address 1 and 0x80. So if that top bit is set, that means we use a register. Equals address 1 and 8, not 8, 0x f minus 8. 15 minus 8 is 7, so 7f dot u. This is what we have to log, so I think that's it. So just the first part of the address. Address 2 mode. There we go. Now we can mix and match our registers or not. I think that's good enough. So we need a register address and an address. We can take those as literal or not. It's where we, yeah, I think this is better. 16, 8, and 0. So when we add a store instruction, we need a register, an address 1, and an address part 2. maybe we go to dovm.h and we say define mode immediate as 0 and mode register as 0x80. I think that's probably clean enough. So add store. So we take our opcode or with our register bit shifted 16, or with address 1, bit shifted 8, or with address 2. I think that's basically it. So if we go to add a store command, that's kind of what we're going for. So if we go to main, we can load immediate, we can store in our VM at register 1. 0 and 0, we can have, where's mode? Go VM mode. Immediate. And register. In theory, we could print. Well, let's put it in at like 13. I should then be able to print out vm.memory at 13. One 42 plus 13. 42 plus 13 is 55. At this point, I'm just kind of curious if this works the way I hope it does. Build. Nope, couple of issues. VM registers. Right, 117. Okay, almost there. 117 incremental types and 2 type register from register.view. There we go. Okay. No op. Load I. 42 stored into 1. Load M. That is not what I wanted at all. Add store. I have the wrong opcode here. Print type int. Okay, now we run. There we go. No op. Load immediately. Button 42 into register 1. Store the contents of register 1 into memory at register 1, so 42, plus an offset of 13, and then I have obviously a print copy paste error. Print as an integer the contents of one and halt. And then a bad print statement there. So let's just clean up our print statements there. Okay, $1 plus 13, print as an integer, contents of 1, halt 1. The contents of memory at 55, which we have zeroed, is now 42 because of this command. Perfect. It's working, it's working. I do want that print statement to actually execute though. Or something like it. There we go, there's the instruction. So we want to do a small thing here. Interesting. Okay, I'll print this anyways. Okay. Good to go. Output as case, default. Okay, I'm going to print this register in a particular way, depending on what our flag says. Printf $. Maybe we're not going to do that. Ooh, there's a few ways we could go about this. This is going to be fun. We're going to print an integer. So modulus d given VM registers at reg dot signed integer. If it's an unsigned, that's easy. If it's a float, that's easy. Character. This might be the more interesting case. Register dot u, and we're just going to take that last byte. That might be good enough. Default error. Invalid print directive. Okay, now we need to add a print command, which we do here. Make, so close. 184. Oh, print. I have a syntax issue. There we go. Print type int undeclared type undeclared. Probably main. Okay, here we go. There we go. So we execute our no-op. We execute a load 42 into register 1. We store whatever is in register 1 into $1, which is 42, plus 13, which is 55. We print an integer, whatever's in $1, which is 42. We halt with return code whatever's in register 1, which is 42. And indeed, we can see after it halts that the contents of memory at 55 is 42. Boom. 42 is an ASCII value. I don't remember. Decimal 42 is a printable, right? I thought I had picked me at the star. So we could, in theory, print this as a character. Boom, there's our character. There's the star. Woohoo! Nice. Okay, are we ready? Here, we're going to do a couple more things here. All these print statements. We need a new line. What we need is to load a new line character in. New line is line feeds. It is decimal 10. We're going to load 10 in, and then we're going to print that as a character. That should give us our new line. Really? 10? CRLF. 10. Boom. So we still have that new line in there, but that's because we didn't make run. Okay, so we can see that this stuff is getting intermixed. Print this character. So we loaded a new line into and then printed it. So here's our new line. So we need to actually have a verbose option. Okay. So our VM needs to know running and verbose. When we initialize, the virtual machine is assumed to be not verbose. Then printf if VM is verbose, then we print. We still have not implemented load from memory. And now that we can store things in memory, we should be able to without too much trouble. That's not a verbosity thing. All right, so make run. It printed that out, and at the end, the memory is 42. We did get our new line and an asterisk. Perfect. And then we can always in main turn our verbosity on. Verbose equals true 1. Make and good. Now it prints out all that nonsense. Perfect. Okay. Not too bad. Part of me wants to log an instruction separate from the execution of that instruction. In case I want to print, so there's two different things we might want to look at. We want to print a program, and we might want to print the execution of that program. They might be different things. Right now they're not, but it's okay. Okay. I think we're doing pretty good. One thing I do want an option for, though. I want an option for hex. Underscore int. Zero x modulus 0.8 capital X, which means nothing aligns quite right anymore. Oops. There we go. Now it all aligns. Basically that's it. As far as I'm concerned. In main, instead of printing a character, we could also print the number 10, which is the new line character, in hex, which would be what, one? No, it'd be A, right? Make run print, and that's just a garbled met. Oh well, not beaver boats. Boom. Oh, we forgot the A. There it is. Because there's no new character. So we should actually do this. There we go. So asterisk, new line. This is the new line character as hex, and then a new line, and then we ended up with 42. Our program is returning the value 10 because that's what we put in that register. Yep, exactly. So I think we're running as far as load, store, print, and operation. I would not mind. I would like it if there was two separate outputs, one which went to the execution and one which went to the console as an output of the program itself. But for now, I think this is good enough to get things started. Where are we at here? Okay. Oh, no, we're not done. What am I saying? We need load. We don't have a load command in here. That's the only one we haven't implemented yet. So let's not get ahead of ourselves. Load. We want to load an address part 1 and an address part 2 into a register. And now that we know kind of what we're doing, this isn't that bad. Load into memory from a register. We just change the ordering around a little bit. So the address 1 bit shifted 16, address part 2 bit shifted 8, and that will be stored into our register. Upload 0x80. So this is, we had a name for this, which is always better if you can have a name for it. VM mode register. It's going to look a lot like that. All right, load. Here we go. Let's grab all of this. This is basically the same footprint we want. So our register, it's actually still going to go in the same place, isn't it? Yeah, maybe we do leave the register at the end. Oh, no. We leave register here. This is what I'm going to do. Or just bit shift one more. Register bit shift 16, or this address bit shifted 8. Yeah, this is probably better. So it's register address part 1, address part 2, even though it means something slightly different. Okay. Dun, dun, dun. Upload M. So we need our register. We're going to have these two addresses. And this is not a store, this is a load memory. We're going to go from memory at address, which will be stored into $sign or $sign U, which is the register. There we go. And that may just be the load command done. Okay. So maybe we do this. Do VM add load M into our VM into register 1. The value that we stored here. So we put 42 in register 1. We wrote that to memory. We printed it. We loaded something else into register 1. Then we printed it out a couple different directions. Now we're going to take what's in memory, and put it back into register 1. So we should be back to returning exit 42. Let's make it verbose again. Make run 55 halt $1 echo. Nope, we're still returning 10. Print load M 1 plus 1 13. Yeah, that doesn't make any sense. All right, we have some ordering issues. This should be $1 plus 13 stored into a register. So load address register. Okay. So it's the upload M. That's confused, or we're putting things in the wrong order. This register Load M. Address 1, bit shift 8. We should get rid of some more magic numbers here. That's not our problem. That's not our problem. Oh. Our load from that address into one. I'll bet that fixes it. Run it. Load memory at $113 into 1. Oh, but $1 changed. That's not 55. So we actually have to do a load in here. Load immediate. We'll do this. Register 1 plus 13, and then store that into register 2, which will be what we actually return. Load immediate 42 into $1. Load memory into 2, halt 2. So echo should be 42 because we got the return code out of register 2. There we go. We've got it. So load immediate, load M. I think we're just done with this. This is good. So we can load, we can store, we can print a few different ways. We can halt and we can do nothing. So that is actually a pretty good start, I think, on a virtual machine. Make, run, and it returned code 42. Nice. So we don't yet have a way to load a file, so I'm not going to be putting out a test file to execute against. That may come after we do arithmetic, bitwise, and logical and comparison operators, operation codes. Although that gets a little bit confusing as well. Think about that for just a little bit. But overall, we are looking in pretty good shape. We have not done a float. We don't really have a clean way to load a float yet. We will. All right, I think we're going to call it there. We have a little virtual machine. Let's go back to this thing. Here we go. So yeah, just a quick recap. We made a virtual machine called the Doe VM. Our structure, it's a von Neumann architecture, so our memory is shared, our runtime memory and our program memory are in the same area. We're using registers, we're using byte codes, we're doing fixed size instructions. We have 1 kilobyte of memory to start with. We're having 16 registers. We decided register 0 is the program counter, so we shouldn't be messing with that yet. 32-bit instructions, 12-bit opcodes, everything else fits in the remaining 20 bits. We do waste some space. And we've implemented all of these. We have a no-op, we have a halt, load, oops, this is a type register. Yes, I think we're there. With a bit of arithmetic, we can load any 32-bit value into this engine and use it. I think we're good to go. All right. Any questions, let me know. Otherwise, we're going to wrap it up there. But we're going to build on this virtual machine so that we have a toy system to help us develop more and more complex systems. Maybe we do need to have a load program Maybe that's what we'll do tomorrow. We'll load a program from file. Load a program from a file. I think we might. Okay. So you have a wonderful evening, and I will see you tomorrow. Bye-bye. You too, Dravest.